and welcome to the 12th episode of Apple Finch Pudding, your gateway into the world of science. Today's scientist is Ruben Van de Vijver, a postdoctoral researcher in chemical engineering at Ghent University. I have a returning co-host for today, which is Robin Van de Casteele, a teacher and criminologist currently working in schooling for people in jail. Welcome, Ruben and Robin. I'm going to dive right in. So my first question is always the same. Do you have a science joke or anecdote or fun fact? It's a question for both of you, but I'll start with Ruben. So Ruben, do you have something for us?
Yes, I have a few jokes and I was thinking about which one to bring, but I think this one may be the most suitable for this podcast. And it's like this. So there's a biologist who's studying grasshoppers. And at some point, he managed to even give commands to those grasshoppers and they would listen to him. So if he would take a grasshopper, put him on a table and say, jump, the grasshopper would jump. So quite impressive. And he was studying all of the things he can change to see how does that affect the ability for the grasshopper to listen to my commands. And at some point, he cuts off the back legs of the grasshopper. A little bit sadistic, but it was part of his study. And he says to the grasshopper, jump. The grasshopper didn't jump at that time. So he wrote down in his notebook, if you cut the back legs of a grasshopper, it becomes totally deaf.
Well, yeah.
And it's a little bit of a stupid joke. It's a joke that I heard when I was even a kid, I think. It's been a long time ago. But I've always remembered that joke because, it's obvious that the reason the grasshopper doesn't jump is not that it cannot listen anymore. But it shows the scientists that if you look at the problem and you already have an idea of what the outcome should be, that it can really bias your hypothesis or your results or how you put it down in a paper. And it's an invitation to really keep an open mind when you look at your data or when you look at science in general. So that's why I think it's still relevant for me and for this podcast in general.
Yeah, that's true. That's true. And there's also a bit the difference between causation and correlation. Because you have the correlation, people that if they can't hear you, or a grasshopper, if it can't hear you, it will not react. But it doesn't mean if it doesn't react that it can't hear you.
Right, that as well. That's right. Yeah, of course. It could just be stubborn. You cut off my back legs. I'm not going to listen to you anymore.
Okay.
But that's true, definitely.
And Robin, do you have something for us as well?
Yes, I was inspired by the Belgian weather at this point. Because it's a lot of gray weather, it's rainy. And I saw in a newspaper an article about why do people get happy when they see snow? And of course, a bit of that is social science, and it's due to nostalgic reasons or due to a reason they want to build a snowman or want to throw snowballs at each other. But a little bit is physics because, of course, snow is clearly white, and it reflects a lot of sunlight. And in this period, you have a lack of sunlight, and that's why it gives you a bit of a happy feeling. So, I thought it was a nice fact to know. It's not that easy. It's not that hard to make that conclusion, but I like the fact.
Yeah, it's very cool. It's a bit like spring sunlight in winter or something like that.
Yeah, indeed.
Okay. I also have a fact for today. So the human body has a little over 200 bones, about 206 or something to be exact. And 1 foot has 28 bones, so about 56 in both your feet. 27 bones are in one hand, so about 54 in both hands, which means that about half of all the bones of a human body are in your hand and feet, which is quite amazing to me.
That's impressive, yeah.
Now we'll go into the science of it all. So, Ruben, you're a chemical engineer, but in chemical engineering, there are a lot of different things you can do. What do you do exactly? Or in what field do you work, to be more precise?
The field that we work in, or how we define it, is called reaction engineering. And that means that we look at really the chemical reactions that are going on in the chemical process. So chemical process exists of many things, starting from you have some crude oil, for example, that needs to be first treated, then put into a reactor, reacted, and then divided again to have all of the fractions that you need afterwards, separation, purification, and so on. But we look only at the reactor, so what really happens on the chemical level, And there we want to know what are the chemical reactions that are going on and how can we change our process as such to have maximal yields with maximal efficiency and so on by really looking at the chemical reactions. So me personally, I don't look, for example, at mass and heat transfer in the reactor or at distillation columns or heat exchange and so on. I really look on the chemical level, what is happening inside a chemical process and really at the individual reactions. And we do this in several ways. I mainly work on the computer, so simulations of those chemical reactions, but I collaborate with people in the lab that are doing experiments as well, but also really on the reaction level.
Okay, so it's really like putting chemicals together and you try to actually calculate the reaction that is happening and see what products are coming out of it.
Exactly, yes. And what intermediates, and if there's a catalyst involved, what happens on the catalyst surface and so on.
Yeah.
So all of those things.
Just a short intermediate, a catalyst. What is a catalyst for our listeners?
So a catalyst in chemistry means that if you have a certain reaction that can proceed as such, so without any catalyst, if you add a catalyst to it, you will speed up the reaction because the reactants will first bind to your catalyst, which will change the properties of the catalyst a little bit, but this will make sure that everything can happen a little faster. So a little faster means you need less energy for it to happen. And then those intermediates on the catalyst will go to this desired product, and the catalyst will return to its original state. So the catalyst doesn't change in properties overall during the process and enables to have everything at, for example, a lower temperature or less harsh conditions for the same reaction to occur.
Do you have some practical examples, like in daily life, where those kind of methods are used?
What kind of methods? A catalyst?
No, not the catalyst, but like the
reaction engine.
The reaction, yeah.
Yes. Yes, there's plenty. I think the most well-known one, which I'm also slightly involved with, but not that much, is what's happening in your car. An engine in a car is a chemical process. So you put in there some fuel, some air mixture, so oxygen, nitrogen. You heat all of that up, that ignites, which leads to your gas, to your engine being able to pump and then to drive your wheels. Inside your engine is actually a chemical process that's going on. And so, for example, what we're looking at right now is you have classical gasoline. Which more sustainable compounds could you add to that gasoline that could lead to the same performance in your car, but with a sustainable fuel, for example, that comes from biomass? That's one of the examples.
So like biodiesels? For
example, yes. So then we look at if there's a new biodiesel, what reactions will actually happen in your engine? Would it lead to some pollutants, some NOx, for example, that you want to avoid, other VOCs, so volatile organic compounds that you want to avoid? Also, what's the behavior, the NOx behavior, which means how clean does your engine still run with those biodiesels? And all of those things are things that we can look at in our computer on the reaction level, and together with experimentalists that are doing some actual burning or engine experiments in the lab.
But in your field, you're not looking at the motor itself, you're looking at the chemicals in the motor, right?
The chemistry that's happening inside the motor, exactly.
Yeah.
Yes.
Okay. So that's the general idea. So the chemical reactions, what is happening, but what do you do exactly? What is your work?
Yes. So my work is twofold. So on one hand, for example, when you look inside an engine, there's many reactions going on. That's a process that happens at high temperature, and it's a free radical process. That's maybe a little bit of a more difficult term, but that means that the chemistry is very fast and there's a lot going on. So we're looking at hundreds, thousands, maybe 10,000s of reactions that are happening simultaneously within 1 second. So the first problem that we have to solve is which are those thousands of reactions that are happening. And that's where I'm working on. So I work on a computer software that we're developing ourselves that starts with, for example, the fuel and air, and will automatically generate all of those reactions that are going on. So that's the first part of what I'm doing. And the second part is for each of those reactions, we have to know some parameters of that reaction. And the main parameter that we need is the speed of that reaction. So the kinetics, the chemical kinetics of each reaction individually. And we have several models to do this, but basically all of those models are done or are based on quantum chemistry calculations. So that's the second big part of my work, is doing quantum chemistry calculations on that type of reactions, as such that we can get the kinetics for all of the reactions that are going on in the process, put all of that together so that we can actually simulate the engine or an entire chemical process as a whole.
So that's a lot of different aspects. I'm going to start with one small question. When you're talking about the speed of the chemical reactions, what speed are we talking about? Is it like a fraction of a second, or is it hours?
Well, that really depends on which chemical process you're looking at. So if we look at an engine, what's happening in an engine, it's all within 1 second. Everything is burned up, for example. So those kinetics are very fast. You might also look at atmospheric kinetics, where things are decomposing in the atmosphere. So for example, you have let's say some NOx coming out of your engine that decomposes and goes, for example, to ozone, things like that. Those kinetics are a lot slower. That can be on the matter of hours. Typically within 1 day, there's a lot of changing, also with the changing weather and temperature and the air and so on. There's other chemical reactions that take much longer even. Those are not really the ones that I look at, but that's also possible. To be clear, that is the macroscopic rate. So that's really what we observe. How fast does the fuel get consumed in the engine? It's not one individual reaction, because if you look at one individual reaction, the time span of one reaction to happen is on the order of femtoseconds. So that's very fast. That's on the microscopic scale. But I look at the macroscopic scale.
Just one thing, you said NOx, that's nitrogen oxygen compounds, or?
That's yes, nitrogen oxides. So that's basically NO and NO2. Okay. And those are harmful compounds which get to some extent out of your engine, and we should try to have it as little as possible created in your engine, basically.
And when you look at the engine and you're talking about a reaction of 1 second, why does the speed matter if it's only a second? Does it matter if it's a second or a fraction of a second shorter or longer?
Okay, that's a good question, but it's quite complex to try to explain it, because once the order of magnitude of 1 second is the order of magnitude of the entire process. So it goes, by that I mean it goes very fast. It's even less than 1 second. I'm saying 1 second to have something.
Frame of reference.
Yes, indeed. But if you drive a car and it goes at 2000 RPM, it means that you actually have 2000 cycles inside 1 minute. So you can do the math of how much one reaction actually, how long it takes for one reaction to actually proceed. But what really matters is not the total speed of the process in that sense, but it's the individual kinetics of all of the individual reactions. So you have those 1000 reactions going on. Some of them dominate, the other ones are maybe less important. And we want to know which one really dominates the process and which reactions are those compared to the other ones. Are those the reactions that actually consume the fuel cleanly to CO2 and water, that we transfer the energy nicely to your engine, or are those the ones that are going to produce some volatile organic compounds that you don't want in the exhaust of your engine, some NOx, some soot to have some particles in the exhaust and so on. Obviously, you have all of them a little bit, but we try to find the ones that are as clean as possible, or we work together with people that develop engines to say, okay, this is the chemistry, can you build an engine around this? This is also a possibility.
Okay, so it works both ways.
It works both ways, yes. And right now, I use the example of the engines because that's an example that's well known to a broad audience. But I'm only working on combustion chemistry and engines a little bit. We're mainly working on some processes that happen in the industry, and there the actual problems of why we want to look at certain reactions is a little bit different. But in the end, boils down to the same: is we want to conduct our chemical process as cleanly as possible, as efficiently as possible, so that we have the less amounts of separation or purification afterwards, as little energy to put in, and so on. So this is a bit of the general trend, but it's not necessarily on engines. So I mainly work on a chemical process that's called steam cracking, which is the main gateway process between the petrochemical industry and the chemical industry, because that's really the process that builds all of the very useful compounds for the chemical industry from crude oil fractions, basically.
The field you're studying in, is it for a long period of time that people are studying the things you do, or is it like recent because of environmental reasons? Because, you know, a lot of those things seem to be, I won't say accidental, but like how an engine works. I don't know if people like 100 years ago when there were cars were thinking about how what will be the result of the oil in the engine.
Right. That's a very good question. So overall, reaction engineering as a field is quite old. So people have been doing that, not necessarily in engines, but in general for a long time. By long time, I mean more than 100 years. So that's really very old. But it has been becoming more and more important, I would say, the last 40 years, maybe 40 to 30 years, for a few reasons. One of the first reasons is that, like you said, an engine, but also most of the chemical industry is based on empirical science. So basically, we're trying out a few things, finding out what works, what doesn't work, without really understanding what was going on the microscopic level, on the level of the molecules. They had some ideas maybe, and sometimes a little bit more ideas than others. But even with that little knowledge, all of the big chemical companies were able to build their plants, able to produce a lot of different chemicals, able to produce plastics, fuels, and so on. But over the last maybe 40, 50 years, some environmental issues indeed came to light, but also the need to do things more efficiently, energy becoming more expensive, companies wanting to be more green, to be more sustainable, and so on. That, and the second big reason is actually the availability of good computers and the availability of good software and good algorithms to calculate chemical data based on quantum chemistry. And I would say this one is actually the biggest accelerator of that research, because before that, most of those reaction rates, so the speeds of the individual reactions, were fitted to some experimental data, but they were not very accurate outside the range of that experimental data. So if you change the temperature a little bit too much, and those values wouldn't make sense anymore. But with quantum chemistry, we're able to calculate reaction rates that are very accurate over a wide range of conditions that are really applicable in general. And that's really speeding up the field. And those values have become more and more accurate over the last 20 years. And I would say the last 10 years, we're able to get close to what experimentalists can do just with computers. And that allows us to simulate everything a lot easier, a lot faster. And that was really the big driving or the big accelerator of this kind of research. But of course, the basic need for that research is doing things more efficiently, also cheaper, to do it cheaper for companies, because if you do it more efficiently, you use less energy, but you also use less of your feedstock, you have less byproducts, unwanted byproducts, and so on.
So that's actually chemical modeling that you do, but how do you know you are right? For example, if I say I combine component A and B, I will get component C, but it's hard to visualize a molecule. So how do you know that you are right? Is it like we also expect the temperature to increase by such amount and we measure that temperature increase so we know we're right? Or how does it work?
So basically, yes, you're right that the model itself is just a model. The model is not always correct, and you don't know if the model is correct. And the only way we can test our models is to validate it against some experimental data. So that's why we collaborate a lot with experimentalists that are doing tests in the lab. And they are indeed, so they're looking at the same chemical process as you, and then they change temperature, and you also change temperature in your model, and you see what changes in your simulations. Does that correspond to the changes and results that they saw in their experiments? You can indeed look at how much heat is being produced, or how much heat do you need to provide for that process to run the actual yields of all of the products that you have, so the main products, but also the byproducts. Can you get those correct? If you can get those correct, then you know more or less that your model is at least doing something right. You'll never know for 100% that your model is completely correct. That is just not possible. But we get close enough to actually do some predictions that help then the design and optimization of real chemical processes. So that it does work, but we never know for 100% sure that our models are exactly correct. And they're not exactly correct. It's always just a model.
A model is always an approximation.
Yeah, indeed.
And are you 100% sure that the model relates to the right component that you're creating? Well, by which I mean that if you have the same temperature input or output, can it be that another molecule is being created that you don't know about?
Yes, that can be. But it depends a little bit on the actual chemistry that you're looking at and how you build your model. As I said, we work on this free radical chemistry, and there the type of reactions that can happen are actually not that complex. There's maybe on the order of magnitude of 10 possible what we call reaction families, so families of very similar reactions. And just by applying those reaction families, we get all of the reaction possibilities, and then we get the products, all of that, and the real products are 99% of the models are part of those that you created just by applying those reaction families. In a few cases, we saw that that's not enough, and you need to look at a few other things. But okay, it's fairly easy. But we also have colleagues that work on organic chemistry, and there the number of possibilities is a little bit more complex. It gets a little bit more difficult to know that you're correct or that you have the correct reaction families, because there you have also the influence of the solvent. You might have some self-catalyzing or solvent catalyzing effects that you don't know of, and so on. So there's many more possibilities. Also, for example, people working in polymer sciences, they know what they're going for, but what's a key parameter in polymer sciences is the size of your polymer molecules, and you might be completely off if you don't have exactly the right model. So there, it is true that you don't always get to the molecule that or that the molecule that you had in your model as a product might not be the one that you see experimentally. Especially for the organic chemistry and for the polymers, it's also a little bit more difficult. But in my case, luckily, because I work with free radical chemistry, it's a little bit more easy. And most of the time we have the correct products, at least in our model. And if we have those products, then if we can calculate the reaction rates with quantum chemistry correctly, which is not always easy, but if we can do that, then the model usually is at least on the right track. And it might need some fine tuning, but it's on the right track.
Two terms you might need to explain: free radical chemistry and polymers. Can you explain what those are?
So free radical chemistry, a radical means, it may be difficult to explain for a broad audience, but a radical is basically an electron that's occupying an orbital by itself. So an orbital, it's even more difficult to explain maybe, is basically some sort of, if you have your molecule, between the atoms, you have one orbital that's bounding two atoms, for example. And those always contain two electrons. You might also have some other electrons in your molecule that are bounded only to one atom, but they're also always in an orbital that contains two electrons. That's just a part of space that contains two electrons. A radical means that that orbital only contains one electron. That's basically what it means. And radical chemistry is chemistry where the intermediate molecules in your process have radical electrons, so electrons that are by themselves in an orbital, and those are very, very reactive. It's difficult to get them, so you need to go to a high temperature. That's why, for example, combustion flames, they always operate at high temperatures to get those radicals. But once you have them, the reactions go very, very quickly. That's what radical chemistry is. I don't know if that's a little bit clear for a general audience.
I think so. Robin, do you understand as well?
The most technical stuff I did not understand, but I get the basics. So I guess for me that's enough to understand the conversation.
Okay.
If I'm not mistaken, it's like, so you have your atom or molecule, mostly an atom, right?
Mostly molecules, because it's part of a molecule, your radical.
Yeah. Okay. And so there's one electron that is like single, and normal they're in doublets, so there's two electrons combined in an orbital, so circling the atom or molecule. But there's one electron that's single, and that is the radical, actually. So the radical molecule, because it has one electron that is very reactive, because it wants to stabilize, right? And it's looking for another electron to stabilize to have two electrons. So that's why it's so reactive.
Yes, indeed.
And then polymer chemistry or polymers.
Yeah, so a polymer, the name that for most people will be very obvious is plastics. So plastics are the most well-known polymers. And what that means is it's a molecule that's built up of many, many repeating blocks. So, for example, polyethylene is one of the most well-known ones that's used a lot in just commodity goods. And that is polyethylene, so many ethylene molecules that have been linked together into one huge chain. Other well-known polymers are wood. Wood is mainly made of lignin, and lignin is a biopolymer, cellulose as well. So those are well-known natural polymers, and synthetic polymers like PET bottles, polyethylene, polypropylene, styrofoam, which is polystyrene. Those are styrene molecules that are repeated one after the other, and that builds a very big molecule, which we call in chemistry a polymer.
Yeah, so you work in the petrochemical industry. And what is your goal? What do you want to create? It's not always for an engine, you say, but when I think of petrochemicals, that's what I think. I think of combustion, I think of cars, I think of maybe boats or airplanes. And what do you do with it in industry?
So there's a few different angles to this question that's relevant for me and for our lab. The first one is that petrochemical means all of the chemical processes that we operate based on fossil fuels, basically on oil, shale gas, those kind of things. Those typically get to petrochemical plants and are divided because that contains many, many different kind of molecules. They're divided based on their properties. A large fraction of that is indeed going to combustion. So that's going to engines, to cars, trucks, planes, boats, all of those things that you mentioned. But another large fraction of that goes to the steam cracker. And the steam cracker is the chemical process that will split up the oil molecules. They're not huge, but they're on the order of maybe 20 carbon atoms. Maybe it can also be 40 carbon atoms, but order of magnitude. And they're split into smaller molecules with 2, 3, 4, 5 carbon atoms. And those are made a little bit more reactive because oil by itself, of course, you can burn it if you add oxygen and heat it up. But besides that, it's not very reactive. So we add some functional groups to it so that it's reactive and can be used in the chemical industry. So this is really to make plastics, to make pharmaceuticals, to make lubricants, to make all possible chemical products that you can think of. Many of them come from this steam cracker, basically. So it's not just combustion. And then our goal really is to make this process more sustainable, cheaper, using less energy. And mainly for the last few years, we have been looking at how can we replace this chemical industry that's really heavily dependent on fossil fuels. How can we replace the feedstocks to something that is more sustainable? So we want to get rid of fossil fuels or fossil resources, basically, because we all know fossil resources lead to a net increase of CO2 in the atmosphere, so more greenhouse gas effects. I don't think I need to explain all of that. So the question is, how can we get rid of that? How can we get rid of fossil resources and move to something that's circular? So we're looking at how can we recycle plastics, for example, and put them back into our steam cracker and back into the chemical industry. How can we use biomass? So we're looking now at the part of food crops that's not edible. So for example, you have corn, but you also have the cob of the corn. What do you do with the cob of the corn? Of course, you can compost. One other possibility is to modify it chemically so that it can also be used as a feedstock to build fuels, but also to build chemicals and everything else. And that way to have some sort of a circular loop. You don't need to put to take any fossil resources out of the earth anymore.
So that's actually then the production also of biogas and stuff like that? Because I think when I hear of biological waste, that's often produced or produces biogas, right?
Yes, but that's really a different process. So that's true. That's also very useful, of course, to create biogas from organic material. But that process by itself is more a biological process than really a chemical process, because that's really the plants are being eaten by bacteria and they produce methane, and methane is in the biogas. But that's a very complex process that involves a lot of enzymes and so on that I don't know the details of those processes.
And I've heard about a hydrogen engine. Is that something that can be applied? Or?
So hydrogen is not really something that our lab, or at least me, focus on a lot. We have a few collaborations with people that are looking at hydrogen. That's also obviously a very interesting route to look at, to replace part of the fossil dependence that we have right now in the chemical industry. But that's a little bit of a different angle than what we're looking at right now. But fully complementary, of course, to what we're doing.
So, but your focus is then one last shot, the biodiesels?
Yes. So, well, biodiesels indeed, but maybe more in general. Like I said, so the non-edible parts of the plants, we apply a chemical process to it, which we call fast pyrolysis, which basically means we heat it up without any oxygen around, because then it would burn. But we heat it up very fast without any oxygen, and it really decomposes to a bio oil. And from that bio oil, we can get some fractions that are useful for an engine and other fractions that are useful for the chemical industry. So that's one angle to it. The other one is, like I said, plastic waste. So a lot of the plastics that are being used in society are single use or have a very short life cycle in society. So what we're trying to do is, instead of burning all of that, because that's what's happening the most right now, is just to burn it off to get some heat out of it, which is something. So you only get heat recovery or energy recovery, but we want to get some chemical recovery. So we want to be able to subtract the chemicals that are in those plastics again, break them off into something useful, and put it back into the chemical industry. So those are the two big routes that our lab is looking at right now.
And if you want to recycle, for example, plastics, I assume you need to add chemicals, but those chemicals that you add also need to be produced. How sustainable is it then to recycle?
So that's a very complex question. It's a good question, but very complex to answer. There's not just one answer to it. It really depends on the source of plastics. So if you really have municipal waste plastics that's highly mixed, dirty, with very different sources, that's a little bit more difficult to have a clear answer to that. But for that, we mostly use those pyrolysis processes where you don't directly need other chemicals. So you just need to apply heat to it, a lot of heat for a very short amount of time. And that will convert it to bio oil and some fractions also of biogas, and there will also be some residue. The residue is pretty much unuseful, but with the bio oil and biogas, you can also do something. It's different from the biogas that you mentioned before, by the way.
But also in case of the bioproducts, you need to heat them. And how do you create the heat? That's also...
Yes. So right now we're looking a lot at electrifying heat or heat from electricity. So for example, electrified reactors. And we hope that electricity can be made from either
renewables.
Yes, renewables. So wind, solar power, and so on. Biogas, which is to some extent which is also renewable. If you really have a fully closed cycle of your CO2, you can also use biogas and those kind of things. Yes. So we obviously know that we cannot solve everything right now and have everything not depending on fossil fuels. So there is still, of course, some of the heating that happens through fossil fuels and so on. But we're trying to reduce that fraction just as much as possible.
Am I correct in assuming that you have two types of experimentalists, like the experimentalists that are creating the biofuels, then experimentalists that are using the biofuels?
Yes.
And you are somewhere in between, like modeling those conversions?
I work with both, basically. I've worked with really primary reactions where you really start from your plastic and decompose it to something, or when you already have decomposed it to something, put it back into another chemical process and see what's happening there. So I've been working on both, but indeed there's experimentalists that work on either or also some experiments that look at combined things, but I work on both.
And your main focus is on the plastics or more on the organic stuff, or really just 50-50?
It's a little bit of both. It depends a bit on the project, depends on the funding at that time.
So you're trying to make everything more sustainable. Have you made some progress towards that?
Honestly, that may be a little bit of my my frustration right now, is that the things that we can see, it takes a long time, a very long time, before something is actually implemented in the industry. So that's I'm still hopeful that at some point I will be able to point at the chemical process and say, okay, I made that 5% cleaner, even if it's just that, or 5% more sustainable. But right now it's a little bit more difficult for me to really see the outcome of my calculations directly in society. But it's obvious that because I work really on the low level, really looking at the individual molecules of what's happening, and there's layers in between until they get to the entire process. And I just have to be patient and appreciate that whole process that goes really from the basic science, which as an engineer, I'm still trying to do basic science and implement that into something that's hopefully implemented into the industry at some point. But right now, I can say that this engine or this fuel or this chemical process is that much more cleaner thanks to me, sadly. But hopefully one day.
Yeah, but I think that's also one of the things or one of the basics of science. The time between inventing something or even discovering something, and the actual implementation of what you found can take ages. And that can be frustrating as a scientist, but even if you don't see it yourself, you are helping solve the problems. And also sometimes accidental. Like CERN developed the internet, which we all use right now, but they didn't create it to that goal. The invention of penicillin was just like, I forgot to clean my dishes and I saw that bacteria aren't growing there.
Yep. So there's actually one more example where something got invented just by luck, and that's by Bakelands, who basically invented plastics. So he put some chemicals together in hopes some sort of reaction would occur. I don't remember the details, but after sitting for some time, that became like a very hard solid. And that's basically the invention of the plastics. So then he saw afterwards that some reactions were happening where indeed all of those molecules were stacking up together to something very large. And once those molecules become very large, they cannot move a lot anymore. That's why they become so hard. And most plastics, as you know, they're also solid, hard substances. So that was also just invented pure from luck, or from actually wanting to do something else and just bumping onto that.
Yeah. So your research will still have an end goal. I'm sure of it.
I hope so. Let's see.
So, Ruben, I have known you for quite a long time, but have you always been interested in science? Was that always your goal? I want to be a scientist?
For most of the time, yes. I was always somebody that was very curious. I was always asking myself questions about the things that I see around me. I remember just being a little kid. I was sitting in bath and I had a bucket and was putting the bucket underneath the faucet, so where the water was coming out. And I was just looking at the bucket, and I always ask myself, the water that goes in, once the bucket is full, does it directly go out? Or does it go to the bottom of the bucket and then lets the rest overflow and so on?
That's advanced thinking for a kid.
Yeah, I don't know what age I was exactly, but I was... Yeah,
well, I assume you weren't 25 when you were with a bucket and bath.
And I remember asking my parents that, like, do you know how long the water actually stays in there? Does it go out directly? And my dad turned to my mom and said, I think he's going to be a scientist at some point. So, and ever since, especially as a kid, I had always I was looking at the world around me and I was always curious, so what's happening? How does this work? And so on. So it's always been in me to be curious and to try to find out what's happening. And now that I know chemistry and I know basically chemical engineers, I also know that that's actually a residence time distribution in this kind of bucket. So it's not that clear. So some of it's like a bit of I think a Poisson distribution of how long the water is. So I have an answer.
But it's an interesting answer, actually.
I'm not sure if it's Poisson, but it's some sort of distribution. So there's an average on how long the water will stay in there. Some of it will go faster. Some of it theoretically stays in there forever because it's really with exponential decay.
Maybe you could yeah, they probably did that, but you can test it like with few drops of a dye with new water that's coming in and see how fast.
Right, but as you will see, because there's a distribution, the dye will just dissolve, and it will become it will, depending on the actual on how the bucket really looks, how deep it is, and so on, and how fast the water is going in. It will probably take up most of the buckets. Maybe the bottom will be a little lighter, but the rest will just have a uniform color, and it's going to be very light in color because it will just dissolve over everything and then pour over.
Okay.
But anyways, yes, I've always been curious. I always wanted to know these things. At some point, I also had other actual professional goals. At some point, I remember wanting to be a journalist.
Okay.
I wanted to be I used to row a lot when I was in high school. I wanted to be a professional athlete at some point as well. I had to bury that ambition quite early, but still, I mean, you know how it is as a kid. But the curiosity in me and really wanting to figure out what's happening has always been a part of my life.
So was chemistry the next logical step, or could it have been physics as well?
Yeah, in high school, so mathematics, physics, chemistry, and biology were really the courses that I liked the most, the subject that I liked the most, that were also the easiest for me. I didn't have to study all that much to get decent grades for them. I always liked the content and so on. And when I was in my 5th year of high school, so in Belgium, that's about when you're 16, 17 years old, I was really into biology, and I actually wanted to be a biochemist. I wanted to study something with biochemistry where you look at protein or enzymes, or really on the molecular level of the human body. And that was really thanks to my biology teacher at that time, because in that year we saw biochemistry as part of the biology courses, and I really liked how he was teaching. It was really inspiring how he was talking about all of those things, and I wanted to be a biochemist. So that teacher, the next year when I was in the last year of high school, taught me chemistry. So you see where this is going.
Yeah.
So during the time of my 6th year, I was like, oh, right, chemistry is actually really fun too. And I was really inspired to do something with more chemistry instead of biology or biochemistry. And I was looking at all of the different options you have at university. So in Belgium, the big ones are, of course, you have chemistry, biochemistry, engineering, where you can go to bioengineering, or where you can go to chemical engineering, sorry. And then you have bioengineering as well, which also has some chemistry in it, depending on which direction you go. And I chose for engineering because that really stays very broad as a subject in general. With engineering, you can do a lot of different things. If the chemical engineering wouldn't be appealing to me anymore, I would be able to change without all that much of changing my skill set and so on. I liked also that it had a lot of math and physics in it. It's not really just chemistry. And also that it's really applied. I like the things that really theoretical science is really nice from a fundamental point of view. And I think that people that do that do beautiful work, but I prefer something that really has some application in the real world. That's why I chose engineering. And when I chose engineering, I directly knew I want to go into chemical engineering. And then I got into reaction engineering during my master thesis. So it was a subject in my master thesis, and I really liked it. And then I just stayed for a PhD. And that's how it went for me.
Yeah. And now a postdoctoral researcher.
And now a postdoctoral researcher, indeed.
Okay. And so you're in academia. I know one of the things that you don't like that much is you want to see the applications of your work, which is sometimes hard. So in general, do you want to stay in academia in long term, or not really, or you're not sure?
That's quite a complex question for me. For a long time, I really wanted to stay in academia. There's a few things that maybe academia are not the best for me. One of them is I really like doing the science and doing the calculations and trying to figure out what's happening. But in academia, you have to write a lot of proposals. You have to sell your work. You have to sell it to funding agencies. That's really important if you want to build a group, if you want to have sufficient funding to actually do science. And that's the part that I really don't like. So I'm lucky right now to be in a group where my promoter, that's one of his main occupations, is really to get money for the group. So he writes proposals. That's really one of his best abilities compared to me. I'm really not that great at writing proposals. So that's why I kind of buried the ambition of having my own group. because I don't want to be constantly fighting for funding or trying to find money with companies or with funding agencies and so on. The second part is also that I don't like the politics in academia that much. I'm definitely not a politician. That's not really my suit. So I really want to focus on the science. So right now, currently, I have a good relationship with my promoter, and he really allows me to just do science and focus on those things, on what I want to do. But I know that it's not a position in which I'm going to be able to grow a lot in the coming years, or maybe at all, I don't know. The other thing is, due to some personal reasons, I want to stay close to my hometown, close to Bruges or Ghent, where I live now, in between both. And around here, there's not a lot of industrial research in the area that I'm trained for. There's a little bit, but it's really not a lot. And I don't know if I would be happy in those companies. So for me, right now, I'm a bit on the fence on where my career is going to go in the coming years. I've always ruled out going to the actual chemical production sites, which is obviously also possible with my degree, but that has never really appealed to me. I really want to be able to do science more than I want to be in a big chemical company and try to work on the plant that's really there. That's just a preference. I can't really explain it in detail.
Yeah, no. I think that's one of the things that comes returns most of the time, because this is the last episode of this year. And what people like the most is the freedom to do science. What they hate the most is the politics. That's like,
right.
yeah.
You were talking about freedom in your job, but like, how much freedom do you have? Can you make a lot of choices yourself, or is the university just telling you what job you need to do?
So that has changed a little bit over time, and it really depends on which project you're on and which instance is funding you at the time. For a while, I had an FWO fellowship for my postdoc, which means that basically that money comes from the government based on one grant, and in that grant you say, okay, I'm gonna work on these topics, but you get a lot of freedom to work on those topics the way you want. And if you see, oh, that's really interesting, and that's maybe part of it from the side, it's not exactly what was in there, you can still focus on that and try to see what's going on. So that gives really a lot of freedom. If you work on an actual project that's funded by a company, that company wants to know one thing, and then you have to work on that thing. So right now I'm funded on an ERC project of my promoter, and that has also quite a broad scope that allows us to do a lot of different things and to be able to really go in detail, and that also gives us some freedom to do it a little bit the way we want. But we have some deliverables, so we have to get to a certain stage by a certain time. But okay, that's that's fine. It's not that restricting on a daily basis, basically. So that gives us a lot of freedom to do what we want, and that freedom is both me as a scientist as well as my promoter, together with his postdocs and PhD students, deciding on what we want to do. So on a daily basis, I get to make some choices that I'm free of, but sometimes, of course, there are some things that need to be done that I do in collaboration with my colleagues. So it kind of depends. But overall, I do not complain at all about the freedom I have. So it's quite nice in academia and in my office how much freedom I have.
Okay, so you're a scientist, but yeah, so you were very curious as a child as well. But imagine you weren't a scientist. Do you know what you would be right now?
There's definitely a few options, yes. In my spare time, a few years ago, I started woodworking as a hobby, and actually really like working with my hands, working with wood, especially working with this natural material. It's really a beautiful material that you can do so much nice things with. I actually even started a little side business with this woodwork recently. I'm doing just some small projects for some customers, but I really enjoy that. I don't know if I'll ever do that full-time, or if it will be something for me to really be full-time on construction sites working with wood. But on one hand, I like that idea. I may still romanticize it a little bit too much, because in practical woodworkers, okay, they have to work in the cold, and it's long days, and it's really sometimes tough labor on your body, and a lot of noise, a lot of dust, and so on. So I don't know if I would actually be a full-time woodworker, but that's one of the options. I also really like to teach. So I teach a little bit at university. Maybe if I wouldn't be a woodworker nor a scientist, I would teach in high school science. I would teach math or chemistry or physics, maybe biology. That would work well if I would be in front of a classroom where the students actually want to learn those things. But I know that in practice, it's also not always that easy, especially if you're in high school. There's maybe a few that want to actually know the subject. The other ones just want to have a passing grade and move on. So that's also why I think I'm not teaching right now in high school. It's really because I don't know if I would be able to handle that atmosphere with the students.
I totally understand. Also, just a small shout out. If you live in Belgium and you need something made in wood, Ruben's your guy. You can contact me or him directly. He'll do a fine job, I'm sure of it.
Thanks.
What are you making? Is it like tables or spoons? There's like a big difference.
It's furniture, basically.
Okay.
Everything that falls under the category of furniture. Yes.
So if you need
Nice.
customized furniture in Belgium, Ruben's your guy.
Thanks.
Yeah, Ruben, we're near the end of the episode. Do you have a take-home message for our listeners?
Actually, yes. It's maybe not directly related to science or to what I'm working on exactly, but it's really with, for example, with starting my side business and also changing or burying my ambition to really be a professor or have a big academic career. It's really what I saw over the last few years, that it's a lot more important to really listen to your gut and what your gut tells you want to do, or it's really giving you a lot of guidance, or at least in my case, it's giving me a lot of guidance on where to go next. And by listening to that, I saw that a lot of stress just fell off my shoulders, that I didn't have to perform that much. I didn't have to perform. I didn't have to go somewhere. I could just do what I was doing right now, some more comfort, some more ease, and just some knowledge in the background that, okay, this is fine, and the way you're going is fine. And even though I basically gave up quite a luxurious position of being able to be a professor, I'll still be fine.
Yeah, I really love it. I think it's a great advice for everyone. This was the 12th episode of Apple Finch Pudding. I want to thank Ruben Van de Vijver for the information and Robin Van de Casteele for the questions. Let's meet again for the next episode of Apple Finch Pudding.